Hello, we're Group 11 and we did the Autonomous Drone Delivery Project. Our group consists of Noah, Mahir, Talon, and Grayson. Our problem definition. Our drone has to fulfill a few functional requirements. It has to be able to fly to a remote location, pick up a payload, deliver that payload to a separate location, and then return to the base station to charge. While completing the tasks, the drone has to withstand outdoor climate and humidity. Our drone can help reduce labor costs by reducing repetitive pickup and deliveries done by people, by autonomously delivering packages to clients. Our drone can reduce unnecessary human contact and meet the increasing demand for delivery services. The drone also has emergency applications and it is able to deliver packages to remote and unsafe locations. The constraint our drone needed to meet was to be able to carry a max payload of 600 grams. The payload needed to be delivered with an accuracy of 1.5 feet horizontally and a vertical accuracy of 5 feet. The additional modifications of the drone needed to cost less than $1,000.
So based off this problem definition, we've come up with a few key hardware requirements that our system must meet. So the system must communicate reliably within 200 feet of the base station at all times, so we can control our pickup and drop off flight plans, receive diagnostic information, and be able to call the system home if there's any problems. The claw must secure the package throughout the flight, so it must be secure, and we need to be able to not drop it at all. The system must also withstand the elements. We came up with the idea of using an onboard system, so on a microcontroller or similar, to be able to communicate with the drone at all times, to pull diagnostic information and modify the flight plans in real time to be able to prescribe a pickup and drop-off location. And the onboard system needs to also control the actuation mechanisms and the package detection mechanisms to make sure that we can safely and securely pick up the package. These requirements were chosen to target the scope of our project, which is really a short-range delivery application. We need to be able to do basic functions, like prescribe pickup and drop-off locations. Our requirements were chosen to target the specific drone in question that we have access to, which utilizes a Pixhawk flight controller with a PX4 autopilot firmware. And this is an excellent platform, but there's a few key problems with it. One of which is that using some external accessories, such as those requiring an ADC read or any sort of custom processing, is very hard to achieve and requires extensive modification to this firmware. Components we came up with for our system ended up being a claw to pick up the package, and we chose the claw to be able to have a well-defined interface with our package. It's easier than using a complicated gripper mechanism or something that requires knowledge of the exact volume of the package. If you just have a predefined interface, like a basket or such, it's easy enough to pick up with a claw. To be able to actuate this claw, we chose a servo motor drive system, which is very standard, easy to control, kind of one signal and power, and works well with our onboard controller. The GPS system we chose was a ZF9P. This is an excellent GPS module that operates under many configurations, and in certain configurations can achieve accuracies up to a few centimeters. So this is a great solution for something that requires the precision of, say, a package detection and pickup system. To determine whether or not we picked up our package correctly, we chose a load cell. It's an easy enough solution that allows us to obtain step response output when we've loaded our drone down with our payload. And based on this, we can determine whether or not there's been a problem with the package pickup or package security, and be able to feed this information back to our ground station for diagnostic purposes, or allow us to pick up the package again. A high-level representation of the system is shown in the following block diagram. Central to our system that we've designed is an STM32 based microcontroller, which allows us to read our analog data from our load cell to see the status of our package pickup, a PWM drive signal to actuate the servo and run our claw mechanism, and is connected to a ground station over a pair of 915 megahertz radio modules that allow data to be transmitted over a simple serial interface. This connects to our drone over another serial interface, and this allows us to, using the Mavlink API, simply feed commands to the drone to tell it where to go, and it goes there seamlessly. The drone is paired with our our ZF9P radio module, which allows us to achieve a high degree of accuracy and be able to tell where we're at all times. So the STM32 controller can read that back from the drone and actuate our pickup mechanisms accordingly. On the ground station side, it's fairly simple setup. With our link to our 915 megahertz radio module, we just have a simple USB to serial interface and a bit of an established API that we can communicate with from our ground station computer to our onboard flight controller and send it waypoints, read diagnostic information, and do some basic testing functionality and basic pings to ensure that communication has remained throughout the flight. To accomplish this hardware design, we've needed to design some software, and this software needs to control the commanding of the drone over our Mavlink API, monitor the ground station at all times for communication link and possible new requests from the ground station for another delivery waypoint. It needs to be able to monitor the position of the drone at all times and be able to actuate the pickup mechanism and detect whether or not our package has been picked up accordingly.
This is our final claw prototype. We completely redesigned it from the last time you saw it in our intern presentation. We did this because we decided to change the drive system from a stepper motor to a servo motor. I spent quite a bit of time tweaking the design in order to correct unsatisfactory tolerances and ensuring the final design could take a beating. But that stuff's boring, so instead I'll just highlight some of the main design features we were able to accomplish in our final design. Our claw arms are 26 centimeters long, which means the arms have a span of roughly 52 centimeters when fully open. This allows the claw to make up for the lack of tolerance the GPS provides. As long as we're able to get within around 50 centimeters lat long and 26 centimeters altitude of our basket, then we should be able to pick it up. Our claw is designed so that it can easily be assembled and all the parts are replaceable, meaning if we break one component, instead of printing a whole new claw, we can disassemble the claw and replace the broken part. This was a difficult task, but I believe it really steps up our overall design and allows for shorter downtime when something breaks. We needed to test whether a ground station could communicate with the drone while flying 200 feet away. In order to do this, we did a simple modular test where we connected two laptops with the same serial communication setup we're using on the drone. I stood stationary on the sidewalk with one laptop while Grayson paced away with the other. We sent each other messages over the link until Grayson was around 300 feet away, and we never lost the link. This test is obviously in one plane, so it's not ideal for testing the max horizontal range of our serial communication. But 300 feet range made us comfortable enough to call this test a pass. We tested the GPS accuracy by marking multiple points on a square sheet and recorded the GPS reading of these points. We later came back outside and tested the same points again. Using a little bit of math, we were able to approximate that the XY tolerance is around 40 centimeters. Keep in mind this is without our RTK ground station. The RTK can improve our tolerance to within just a few centimeters. We were also able to roughly see the ballpark XY tolerance that our onboard GPS provides when we did our autonomous flight testing, where we had the GPS module on the actual vehicle. The drone was able to take off from our launch pad, execute a flight plan, and then land back on the launch pad within about 15 to 30 centimeters XY of its original takeoff point. Since we are dealing with expensive equipment, roughly $2,000, we quickly realized it's not really an option to send the drone into the air with a flight plan built by undergrads. We discovered there's an open source robot simulator called Gazebo that features advanced physics. The Gazebo simulator is widely used in university research and has proven itself in underwater, ground, and flying robots. We built a drone in the simulator that runs the same Mavlink protocol that our real drone does. In other words, the Gazebo drone is a software replica of our real drone's hardware, and we're able to see how the drone will react to our flight plan without risking damage to the real drone. We discovered that the time spent figuring out the simulator was well worth it since we crashed our Gazebo drone many times.
After gaining confidence with our results in the modular testing system, we were able to put it all together onto the drone and proceed with our testings here. With the drone in flight, we were able to test our positional accuracy, and since the drone is flying, that means the communication systems were also working well. As well, the temperature conditions that we were flying in were about minus 18 degrees that day, and the winds were around 20 kilometers per hour. Since we were satisfied with the results of our basic tests, we ran a few flight plans that would mimic a standard pickup and drop-off routine. Some limitations that our design faces is that it's an open loop system, so there is no visual detection of our package being acquired. The interface leaves more to be desired because there is no GUI, so we can't readily read our information in a efficient manner. The communication system range is relatively low, so we would like to improve this with a better radio and a bigger battery so we could deliver our package farther and more accurately. And that in order to implement our solution, a GPS isn't good enough. There needs to be an auxiliary system in place, such as an onboard camera with a computer vision implementation, a depth camera with point cloud for image recognition, and RTK, just to name a few examples. We learned some very valuable lessons in time management and estimating time to meet deliverables. We found that every step took longer than we anticipated, with unforeseen roadblocks. An example of this is that when we ordered a servo for our project, the first servo did not want to hold its position, and then after we ordered a second servo, we found that it was a different form factor, and that presented a lot of compatibility issues. This happened over the course of weeks, and there were many issues that came up just like this, which were very frustrating and time consuming. As far as experience goes, or lack thereof, getting up to speed with software, hardware, and firmware alone took a lot of time, and learning how to order parts that work with our current system is also a challenge. Some future plans that we have for our solution is to implement a computer vision system with either a depth camera, which creates point clouds, and we'll use image recognition for that. Some cheaper alternatives to that would be using physical markers and using just a normal camera to detect physical markers like Aruco markers, QR codes, or even a color filter like an HSV filter. And we would also like to improve our altitude sensing by using a LiDAR sensor or a sonar sensor or something of that sort. A special thanks to our clients Ryland and Torben for providing us with this project, and we would like to welcome any questions you might have.